Yo, 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 welcome to the last unit in chemistry, oxidation reduction reactions. What do we know about reactions so far? Well, we've gone over acid-base reactions, hydrogen ions and hydroxide ions, precipitation reaction, as you guys can see in that picture with the yellow solid forming when two solutions mix, and the last type, oxidation reduction. Well, we haven't gone over it yet, and that's the last type of reactions we need to know. Oxidation reduction reactions involve the transfer of electrons. Some examples include providing us with energy from food. Example would be cellular respiration, and then provides electrical energy in batteries, and occurs when iron rusts, as we see in the equation below. Iron metal, solid, reacts with oxygen gas to produce iron 3 oxide. Oxidation reduction reactions are also known as redox reactions. Oxidation and reduction always occur simultaneously. Electrons must be transferred from one reactant to another. And when these electrons are being transferred, we need to have a method in order to keep track of where these electrons are going. And so a method would be using oxidation numbers. So oxidation numbers are used to keep track of how many electrons are lost or gained by each atom in a molecule or compound. So the definition of an oxidation number is the charge the atom would have in a molecule or an ionic compound if electrons were completely transferred. So that right there, y'all, is the definition of oxidation number. So next, we have the rules for assigning oxidation numbers, and the first one is that free elements or uncombined state have an oxidation number of 0. That's right, 0. All diatomic have an oxidation number of 0 as well. So let's look at some examples. We have sodium by itself, beryllium by itself, potassium by itself, lead by itself. All of those are considered to be free elements. So they have an oxidation number of 0. And then hydrogen gas, oxygen gas, H2 and O2 respectively, have an oxidation state of 0. Number 2, in monatomic ions, the oxidation number is equal to the charge on the ion. So let's take a look at an example. We have lithium with a positive charge, and that would be considered a positive 1 on oxidation number. We have iron with a positive 3, so its oxidation number is 3. And then oxygen here with a negative 2, thus a negative 2. But Mr. Tran, where are we getting these numbers? Well, good question, Billy. Let's remind ourselves where we got some of these numbers. So again, using the periodic table, we told y'all at the beginning of the year the oxidation number or the charge that these elements would have when combined with others. So this one would be a positive 1. So all of these guys, positive 1, positive 2 here, positive 3. And then starting with nitrogen, negative 3, negative 2, and negative 1. Okay, so that's where we got lithium to be positive 1 and oxygen to be negative 2. And so let's move on with the rules. Number 3, the oxidation number of oxygen is usually negative 2, but there's an exception to this rule. When it is in hydrogen peroxide here, it is considered to be negative 1. Number 4, the oxidation number of hydrogen is positive 1, except when it's bonded to metals in binary compounds. Then its oxidation number is negative 1. So that's the exception to the rule. Let's look at our example. As you can see, hydrogen is bonded to nonmetals here, so its oxidation number would be positive 1. But when hydrogen is bonded to metals, sodium and calcium respectively, hydrogen's oxidation number is -1. Number 5. For covalent molecules that do not contain hydrogen or oxygen, the more electronegative atom is assigned the negative oxidation number it usually has in an ionic compound. So let's remind ourselves of the electronegativity trend. As we go from left to right, we know that electronegativity increases. And from top to bottom, we know that electronegativity decreases. Okay, so let's take a look. We have phosphorus and chlorine. So chlorine is a halogen located here. Phosphorus is not a halogen. It's somewhere here. And obviously, we see that chlorine would be the more electronegative element. So it gets its normal oxidation number of -1, where phosphorus doesn't. And then sulfur, same thing. It is more electronegative than carbon, so it gets a -2 charge, oxidation number. Moving on, number 6. The sum of the oxidation numbers of all the atoms in a molecule or compound is 0. The sum of all the oxidation numbers of atoms in a polyatomic ion is equal to the charge on the ion. So let's see what that means, y'all. I'm going to give you guys a basic example. We have sodium chloride. Notice that there's no charge or overall charge on this compound, so its overall charge is 0. The respective charges on each atom would be a +1 for sodium and a -1. When we add those up, y'all, it gets a charge of 0, as seen in the actual compound itself. It has no overall charge. Then, when we take a look at a polyatomic ion, for example, nitrate, it has an overall -1 charge. And if we were to determine the oxidation numbers for each of the atoms there, we know that the charges must add up to -1. So let's take a look at examples here, y'all. We have oxidation numbers of all the atoms in CF4 and HCO3 negative. And so that, y'all, we're going to work on the side real quick. So we have CF4. So we don't see an overall charge there. And then fluorine is the more electronegative, so it gets this -1 charge. There's 4 of that, so the overall oxidation number of fluorine would be -4 because there's 4 of those fluorine atoms there. And then we have carbon. So in order for this -4 to be canceled out to have an overall charge of 0, carbon's oxidation number must be a +4. And when we add them up, we do see that it is indeed 0. And then we have bicarbonate ion. So its overall charge is a -1. So we assign these oxidation numbers, y'all, using the rules we know. So we know that oxygen's oxidation number is -2. Hydrogen is a +1 when it's bonded to nonmetals, and they're all nonmetals here. And we're left with an unknown for carbon. So what we do know is that it must all add up to a -1. So -2 times the 3 gets me a -6 oxidation number overall for oxygen, +1, and I'm going to make that question mark into an X here. That's a -1. So the oxidation number for carbon, once I simplify the side of the equation, I solve for X, it looks like the oxidation number for carbon is a positive 4. Okay. So if y'all were like, whoa, 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 Mr. Tran, that was way too much. Well, there are steps on the next slide that you guys can definitely follow. So let's go. Okay, so what happened on the previous slide was a little confusing at the end. We're going to tell you guys a clear, methodical, step-by-step process of how to find the oxidation state. So the question here is find the oxidation state of CrNK2Cr2O7. So I'm going to color code it, and in your notes, y'all, you guys should have the same table. I'm going to start off by listing the sides here, element, and the subscript. So that subscript, y'all, would be the small numbers next to the element. So K would be 2, Cr2, and then O7. The oxidation state of one atom would be the charge it would have if it was in, an ionic compound or a molecule, or whatever the case may be. So oxygen, the rule is that it has a -2. Potassium, if we were to look on the periodic table, has a +1 if it was in an ionic compound. And the only one we don't know and we're looking for is chromium. So +1 for K, Cr is question mark, and oxygen -2. Then the sum of the oxidation states, we multiply these two, y'all, together to get this bottom row. So I want you guys to write that down. Draw an arrow to the side of your box and write down multiply. And when we do, we get the bottom. So 2 times 1 is 2. 2 times question mark. I'm going to change that question mark to an x, so it's 2x. And then 7 times -2 is a -14. And when we add it all up, we take a look to see if there's an overall charge. Guess what, y'all? There isn't. So it is indeed a 0. Okay. So now we simply solve for x. So using the previous table, I'm going to rewrite it real quick. So the oxidation state is +1. We don't know x, and -2. So when we multiply, we get 2 plus 2x minus 14 equals the overall charge is, again, there's no charge, so a 0. And that's how I have this line. Okay, if I can connect this line here. So we solve for x, y'all. So I combine my like terms. 2 and a -14 gets me a -12. Move 12 over onto the other side to try to get x by itself. To get x by itself there, we divide both sides by 2. And we get the oxidation state or number of Cr is a +6. Determine the oxidation number of the bold-faced underlined element in the following formulas. So that's what we are going to do. We are going to apply the steps we learned earlier. So I'll write down the oxidation number on top, the charge. So sodium +1. They made it easier for us by telling us what to solve for. So that's x. And oxygen -2. Multiply down. And -2 times 4 gets me -8. I don't see an overall charge, so it's a 0. Simplify. To get x by itself, I add 7 on both sides to get an oxidation state of +7. Okay, for the next one, x for nitrogen, and then hydrogen gets a positive 1 if it's bonded to a nonmetal, which is true here, positive 1. So now we multiply. X plus 1 times 4 gets me 4. And then the positive 1 here is a 1. So to simplify it, I subtract 4 on both sides, and I get x equals negative 3. Okay, last but not least, y'all, write down the oxidation number or charge, positive 1, negative 2, and x. We multiply, so 1 plus x minus that negative 2 times 3 gets me 6. And then it has an overall charge of negative 1, so negative 1. So I simplify on the side of the x, combining 1 and negative 6 to get me negative 5. Then I add 5 on both sides to get x equals positive 4. Now that we are masters of finding or assigning oxidation numbers to the atoms in a compound or molecule, we're going back to redox reactions. So we will use the acronym oil rig to help us with key terms. So the term oil stands for oxidation is loss. So that's the oil. Oxidation is loss of electrons. Then rig is reduction is gain. So R-I-G, right? Gaining electrons. This will help y'all out when we are talking about half reactions tomorrow. So oil rig. Whoa, whoa, whoa. So this is the last slide for today. We are going to go over oxidation and reduction, starting with oxidation first. Oxidation is characterized as a loss of electrons. So what is losing the electrons? We'll get to that in a moment. So this loss of electrons means there's an increase in oxidation number or becoming more positive. The electrons are located on the product side. So like I said before, the reducing agent would be the thing that's losing the electrons and is oxidized. This can be illustrated with this half reaction. Notice that tin becomes a positive 4 ion, meaning that it lost electrons, 4 electrons to be specific, and you guys can see that indicated here. So this arrow I like to think of as creating, producing. And so tin right here is releasing the 4 electrons from it, thus having a positive 4 charge. Tin right here, y'all, would be the reducing agent. It lost 4 electrons. Okay? And then over here, reduction, the opposite of oxidation, gain of electrons. And this can be seen as a reduction in the oxidation number or becoming more negative. Doesn't mean that you'll see a negative sign. It just means there's a decrease in the oxidation number. And then the reactants would be the place where the electrons are located in a half reaction. Oxidizing agent would be the one that is gaining the electrons. So looking at our example here, this right here, y'all, would be, okay, if my pen would work, one more time. So, would be the oxidizing agent. Notice that the electrons are on the reactant side. This to me right here means that this ion is gaining 1 electron, so I have to subtract that positive 3 by 1 to get a positive 2. So there's a reduction in that oxidation number. Notice it's not a negative number, but a decrease in a number. So we know this is a reduction. Okay, y'all, we're going to go over half reactions tomorrow. Have a good one.